rigidity triangle groups inside the finite space.
Thank you, Nathan. Okay, there we go. I haven't given a talk without coffee in at least 25 years, so I have no idea how this is going to go. So it's really a great pleasure to be in Montreal. I like it here very much. It's a long time since I was here. It's nice to see many people I haven't seen in a long time. So this is a, oh, I better start my timer. This is a talk. This is a talk about this a three manifolds conference, right? So the three manifolds stuff I'm going to assume you know. The profinite rigidity stuff. I apologize if you've heard me talk about this before. Fritz Grunewald got me addicted to this almost 20 years ago now. But I'll sort of go through, I don't want to turn into a colloquium about profinite rigidity, so I'll go pretty quickly through the profinite rigidity background and advertising. Oh, thank God for that. Thank you. Thank you. Oh, it's better. I'm sorry you don't have one. I'll go pretty quickly through the advertising in the background, and then when I come to the more substantial newer stuff, I'll slow down. Okay, and the main results I'm going to talk about, there's various co-authors whose names will appear, they're the dots, but the main results I'm going to talk about is joint work with Alan Reed and Ryan Spittler, who's here, is going to talk after me. I'm also going to skip over something in the middle because Ryan's going to do it in more detail. Okay, so here's simple question, right? This is what got me addicted years ago. To what extent is a finitely generated or finitely presented group determined by its finite quotients, right? Sort of a kindergarten math kind of question, if you go to the right kindergarten. And it's a basic question, and it sort of gets interesting because there's a lot to say about it, right? But the real thing I want to get at today is why have I distinguished between finitely generated and finitely presented? Okay, and this is newer, and this is something I find surprising. So when I say groups, I'm not going to be so interested today in building pathological things. I want groups that really arise in nature, and I mean our nature, right? The low-dimensional world of hyperbolic geometry and 2 and 3 manifolds and orbifolds. For example, that group. So I'm going to keep using that group as a prime example, right? The 3-3-4 triangle group. Oh, such a lovely picture. I was conscious that particularly people like Nathan in the audience, I steal these pictures off the web and I don't know who did them. So if I've stolen a picture of yours, I apologize in advance. And so the themes are, the groups I'm going to talk about are coming from low-dimensional topology. I want to emphasize and try and convey to you different sorts of profinite rigidity. Okay, and I really want to convey that. And then I want to explain this sort of newer thing, the importance of finiteness properties, the difference between finite generation and finite presentation in particular. Okay, now just to make you feel good, I'll remind you what residually finite means. It means your favorite non-trivial element survives in some finite quotient. Okay, and lots of the groups you come across in nature are residually finite, so finitely generated linear groups over any field. You can do basic things like take direct products, free products. You can pass to overgroups of finite index. You can take inverse limits, but you can't take direct limits. For example, take a direct limit of cyclic groups. The rationals isn't residually finite. You can also take more general extensions. Now, I want to emphasize this. You might think, why is he doing this? You'll see later. If A and B are residually finite, then it's a reasonable guess that the extension will be. Okay. Now, that is actually true as long as everybody's finitely generated and the center of A is trivial, right? And that's the point I want you to remember, the center of A being trivial. Then there's no problem, but centers cause you problems, as we shall see. The fundamental groups of all 3 manifolds and orbifolds cause residually finite. That's not a trivial fact, right? That's a consequence of geometrization. Famously, Donny and friends gave us a huge number of extra residually finite groups. I think from my point of view, now one of the great things about sort of Donny's work is the fact that lots of things are seen to be residually finite that you don't see from the definitions. Okay, it really vastly increased the world of geometrically interesting residually finite groups. You might say it goes via linearity, but still lots of things we didn't know before were residually finite. Take the automorphism of a residually finite thing, it'll be residually finite again, but not if you take the outer automorphisms in general, right? That's another interesting thing, and that's kind of to do with centers again, right? Centers are causing a problem. And the really striking thing about centers is if you just do the tiniest little violence to a nice group, that is, you take the symplectic group and this called metaplectic group, there's a non-trivial central extension with just a little z mod 2 here as the center. Deligne famously showed that's not residually finite, right? That z mod 2 dies in every finite quotient. So that's supposed to be alarming, right? That tells you centers really pose you a problem. And since I'm going to be talking about Seifert fibred spaces, that's a bit scary, right? Never mind. So the profinite completion. So you're just trying to study the finite images of your group, those gamma mod n, and finite index normal subgroup. But instead of just putting all the finite quotients in a bucket, the grown-up thing to do is to order them, right, by the natural ordering. If you factor out one finite index subgroup, then you factor out a bigger one. There's an arrow from the first to the second. So they naturally form a directed system. Take the inverse limit of that system, and that will remember all in one mathematical gadget all of the finite quotients, right? So that's the grown-up way to think about the set of all finite quotients of your group. What you gain, well, you kind of took sort of kindergarten toys, finite groups, and then you built them into something kind of uncountable and scary. But you gain a lot by doing this, right? First of all, it's an inverse limit of compact groups. So the inverse limits itself naturally a compact topological group. Crucially, it's got the same finite quotients as the group you started with, right? So you start with a finite generator group, you build this uncountable gadget, but it's residually finite, but it's got the same finite quotients as the group you started with. Okay, so you don't lose much in this talk by just thinking of that as meaning the set of finite quotients. Okay, it's got more structure, but you don't lose much by thinking of that. There's an obvious map from gamma to profinite completion, and that will always have dense image in this topology. It'll be injective if and only if the group's residually finite, right? Because you're obviously not going to remember the stuff that dies in every finite quotient. And this is all very functorial. So you've got a morphism of discrete groups. It induces a continuous morphism of profinite completions. As I said, they have the same finite images. It's so good I said it twice, right? But then there's this nice thing that various people proved independently in the 1980s. For finitely generated groups, two finite generated groups will have the same set of finite quotients if and only if their profinite completions are isomorphic as topological groups. Okay, I've actually sort of sneaked in there a very deep theorem of Nickloff and Siegel that says every map from a finite generated profinite group to a finite group is continuous, but it's true. And so this is really true, right? So this direction is obvious. This direction needs argument. Okay, but you can honestly just think of the gamma hat as the set of finite quotients in the statement of theorems, and the theorems remain true. Okay, I've deliberately talked while that's on the board just to get you used to gamma hat. Gamma hat will just keep appearing as the profinite completion of the group. Okay, now I like my blob picture. This is /blob PDF. It's important to realize that we're going to think about groups that have the same profinite completion. Right? Now, it's important to realize that when I write something like that, the two groups have the same set of finite quotients, there's no implicit map between the discrete groups. That's really an important thing. You're going to have to work hard to get any map between the discrete groups. Okay, but there is the blob picture. So, you know, they've got this common profinite completion with maps to it, right? And just so this is some big blob, and you think, and these are dense subgroups of this common object. And so you can transport information across the blob, right? So this is supposed to be a cartoon of the lattice of finite index subgroups in this guy, right? You take the closure of each one in the blob, and then you intersect with the other guy, and you come out on this side, and you have exactly the same cartoon of the lattice of finite index subgroups, right? All the inclusions are the same, all the indices are the same. If something's normal when you start it, it's normal when you finish, it preserves conjugacy and so on, right? So you have the same set of finite quotients, but implicitly, this isn't a trivial thing, but implicitly you have the same lattice of finite index subgroups too. So it's got a lot more information than just having the same set. Okay, and you know, if you take one here and you take the corresponding guy over here, they will have the same profinite completion. So you get, and this is useful information thinking about these lattices. The blob. Okay. Right. Now, what we're really interested in is proving absolute profinite rigidity theorem. So finite generated residually finite groups, profinitely rigid in the absolute sense. If whenever you've got another thing with this, so better be, let's say we'll stick to finite generated residually finite groups. If they've got the same profinite completion, they actually have to be the same. Okay, so you can recognize the group from its set of finite quotients. That's what you want to prove, things like that. Now, along the way, of course, when you're trying to prove things isomorphic, you're looking for invariance. And so we're also interested in what properties of groups are and are not profinite properties. And ask me questions at some point, right? Just, is that a profinite property? Is that, it's kind of, this is a great sport. This can keep you, it can keep you in gainful employment for many years, right? You say a group property is a profinite property if whenever two things have the same profinite completion, if one has the property, then so does the other one. The obvious definition. Okay, so let's think about some profinite properties, profinite rigidity. Easy exercise. Z to the R is profinitely rigid. Okay, so you take some other finite generated residually finite group with the same set of finite quotients, then the claim is it actually has to be Z to the R. Okay, now, so this is probably the only proof that's going to appear in this talk. Well, first observation is gamma has to be abelian, because otherwise, if you had some non-trivial commutator, then in some finite quotient, that commutator would survive. So you'd have a non-abelian finite image, right? So you know you're abelian, and that's the crucial line, because instead of just trying to think about all the universe of all wild groups out there, we're suddenly only thinking about abelian groups. And then for finite generated abelian groups, it's easy to recognize what they are from the finite quotients, right? For example, you can recognize the rank by just thinking that for all p, you have to map onto Z mod p to the m, right? And that's a statement about finite groups, so it's a profinite invariant. Okay, so free abelian, finite generated abelian groups are profinitely rigid. So your next thing might be, you know, so as you slowly give up some commutation, you think about nilpotent groups. That turns out to be a much more subtle problem. And there's a lot of work on this in the 70s and the 80s. Higman was interested, Remez-Lennikov, Pickel, who was a student of Baumslag, and a series of beautiful papers by Grunewald and Siegel. It turns out that, so for the same sort of very easy argument, if a group's got the same finite quotients as a nilpotent group, then that mystery group has to be nilpotent of the same class, right? So then you're just inside the class nilpotent groups, which ones have the same finite quotients. It turns out only finitely many groups can have the same finite quotients. That's finite genus, but they can be, but you can get different non-isomorphic nilpotent groups. We'll see a couple in a minute, which are non-isomorphic but have the same finite quotient. So already in nilpotent groups, there's interesting things to say. And then all hell breaks loose surprisingly quickly. So the first to realize this was really Serre, who has this beautiful little note in Compte Rendu in 1964, when he was using the profinite completions of fundamental groups, in this case, thinking of it as the étale fundamental group of a scheme, to give examples of smooth complex projective varieties where the underlying scheme is the same, the Galois conjugates. We were hearing about Galois conjugates yesterday, but the topological realizations are different. And the way you see they're different is you see that the fundamental groups are different. And these groups are sort of, they're virtually abelian groups. You've got some free abelian group acted on by some finite cyclic group, but the action's different, and you get different groups with the same profinite completion. That's what Serre did. Now, Baumslag thought about that and sort of boiled it down to its absolute essence and gave the sort of simplest possible examples. And I love these examples. So that group looks remarkably like that group, right? Z mod 25 acted on by Z. There, it's acting as multiplication by 6. There, it's acting as multiplication by 11. 11 is 6 squared, mod 25, right? That group can be embedded in that group as a subgroup of finite index and vice versa. They also have but these are also the easiest examples of groups I know where if you cross them with Z, they become isomorphic. They're stably isomorphic. But they're not isomorphic. You can just do that on the back of an envelope if you still have envelopes in your world. Right? People used to do things on the back of cigarette packets. Then everyone stopped smoking. They did it on the back of envelopes, and now there's no envelopes anymore. That's a complete tangent. This is what happens if you have no coffee, right? Anyway, the point is, so here's some, as soon as you take a little step away from cyclic groups, you lose profinite rigidity. Okay, so you might lose hope at this point and think, well, then nothing, well, what the hell's going to be profinitely rigid apart from trivial examples? Another worrying example is a direct product of two free groups, which I'll keep coming back to. That's not profinitely rigid. Okay, there are finitely generated residually finite groups that are not isomorphic to F cross F, but they have the same finite quotients. Well, I'll come back to that because it's an important prototype. And then this question, which often attributed to Remeslennikov, we don't know, are finitely generated free groups profinitely rigid? Right? That's really so the sexiest problem in the field. Right? That's really generated a lot of good math thinking about that problem. And it's going to go on doing it. I'll say something more about it later. Okay, but so in this direction, so so far we've sort of only got things like groups satisfy a law, things like abelian groups. Are there any full-sized groups that can they're profinitely rigid in the absolute sense? Where full size means grown-up proper groups. So they have to have a free subgroup, for example. Okay, so you got to stop things from having group laws. So is there any such thing? Right, now might three manifolds save us, right? So we all know in this room that three manifolds are wonderful things and three manifold groups are special things. So I didn't mean that in a technical sense. The three manifold groups are wonderful things. So might it be that in the world of three manifold groups, everything's profinitely rigid? And there's these examples that actually go back to the 70s. I don't know whether to say Steber or Stevie. I don't know where he was from. He was a student of Baumslag, who gave these examples. So this is the first time where you see a little bit of arithmetic coming in. There's some class field theory here. And those matrices, there they are, they're obviously different. Right? They're not conjugate in GL2Z, but they are conjugate in any finite quotient of GL2Z if you reduce mod M. Right? And because of that property, if you form the torus bundles with those holonomies, you get different torus bundles. You get two Sol manifolds, but the profinite completions are the same. Right? So even in, I really like this picture. So if somebody in this room did that, thank you for that one. So for Sol lattices, right, you don't have profinite rigidity. You can have different guys with the same profinite completion, same finite images. A similar trick to Baumslag's trick with that little virtually cyclic group, Hempel pointed out you could do that with circle bundles over the circle, sorry, surface bundles over the circle with finite holonomy. And so you can get manifolds, pairs of manifolds with H2 cross R geometry. The manifolds are different, but the fundamental groups have the same finite quotients. On the other hand, there's a nice theorem of Wilks, which I'm going to use later on, which says for SL2R manifolds, you do get profinite rigidity. So if you've got two fibred spaces with SL2R geometry, if they have the same finite, if the fundamental groups have the same finite images, then the manifolds are homeomorphic. Yeah. I'm going to talk about that. Yeah. Well, the short answer is it's not known, but in some cases it is. That's where I'm going. Okay, and now here's some good news about three manifolds, right? So there's some lovely work of Wilton and Zaleski that says that the profinite completion can recognize a lot of the structure of the three manifold, right? So if you've got two three manifolds and their fundamental groups have the same finite images, then they'll have the same prime decomposition. Well, they'll have the same number of factors in their prime decomposition. The prime factors will have the same geometry, right? So we've got three hyperbolic pieces here. You'll have three hyperbolic pieces here. So that's really lovely. So the structure of the three manifold at that level is really seen in the finite quotients of the fundamental group. They rely on, and there's a similar statement to the JSJ too. The JSJs will look the same as well. that relies in part on a really nice piece of work by Heiken, which is really striking in many ways, who proved that for compact free manifolds, fibering over the circle is a profinite invariant, right? So you've got two manifolds, and their fundamental groups have the same finite quotients. If one is fibered, then so is the other. So that was known for non-empty boundary. Myself and Alan Reed and Michel Boileau and Stefan Friedel had results, but the Heiken's theorem is really the last word on that. Okay, so we have some good news for three manifolds, but we had these worrying examples of three manifolds that aren't profinitely rigid, right? And those examples were these torus bundles over the circle I talked about, Sol geometry. Now, a miracle happens. Oh, we like miracles. If you puncture the torus, the ambiguity goes away, right? So for torus bundles over the circle, the profinite completion can't tell which bundle you've got. If you puncture the torus, then of course the mapping class group is still SL2Z, but now the profinite completion of the punctured torus bundles do recognize which bundle you've got. So you even get profinite rigidity amongst all three manifold groups, right? So you puncture the torus, all of a sudden you get rigidity, right? So in this case, these will be pseudo-Anosov maps on the punctured torus. So these will be hyperbolic manifolds. Okay. So moving towards hyperbolic geometry, we start getting more rigidity. Okay, again, there were earlier results like this, like for the figure 8 knot complement, myself and Reed and Boileau and Friedel. Okay, right. So that's the background, right? That's all the history I'm going to talk about. Now I'm going to talk a bit quicker. Is that clock going up or down? Down. Oh, good. Let's talk about three types of rigidity. And I've sort of tried to the preamble is supposed to make you think about this, right? So what we'd really like is absolute profinite rigidity, where you've got a finite generated residually finite group gamma. You say it's profinitely rigid in the absolute sense. Whenever you've got anything else, well, you have to be finite generated and residually finite. Anything else with the same finite quotients actually has to be isomorphic to it. So I always like to think of lambda as the group that you find in the gutter, right? It's this dirty group you find in the gutter. You know nothing about it except it's residually finite and finite generated. You clean it up and you find it's isomorphic to the classical example, right? So you find a group lying in the gutter and you clean it up and it seems to have the same finite quotient as, say, SL3Z. You say, oh God, is that really SL3Z that's being lying there in the gutter all the time? Right? So that's the absolute, but you know nothing about it. It just comes to you without context. Right? Proving something's profinite rigid in the absolute sense, that's going to be much harder than the sort of things I was talking about on the previous slide, where I put myself in a context where I've got structure like abelian groups or three manifold groups or whatever, where you know what the whole class of groups is, and you can use what you know about the class of groups to prove rigidity within that class, right? So for example, here, I could have put three manifolds here, but here I was just taking the class of punctured torus bundles over the circle and just asking questions about that class. In the absolute profinite rigidity, you've got to look amongst all groups. And then you've got to try and reduce to a relative problem where you say, well, at least I can prove some theorems, and then I'll prove a relative profinite rigidity theorem where I'm in some class of groups and say within that class of groups, my favorite group is profinitely rigid. Okay, everyone got the difference. So this is much harder, right? You're out in the wild world, you found a group in the gutter, you got to try and clean up your group and get it into a nice class where you've got structural theorems about groups in the class to help you. And then there's something that looks at a kind of where you're in an even more controlled situation. So here with the still, remember the blob picture, you know, there's no map between the discrete groups to start with. You've just got their finite images the same. You've got to somehow manufacture not just an isomorphism, but you first got to manufacture some morphism between these groups. Right? What happens if you're given that morphism already? So this is why I first got interested in this subject. This is what Grunewald got me interested in. So this old question of Grothendieck from 1970. You've got a finite generated residually finite group. Then suppose you've got a subgroup, you've actually given the morphism, and you're told that that morphism induces an isomorphism profinite completions. Does that only happen in the trivial way? Does that only happen if the original morphism was an isomorphism? Okay. So you say a group is Grothendieck rigid if that's true, right? If when you got a morphism inducing the isomorphism of profinite completions, then actually it's just the isomorphism. So that's the weakest property of all somehow. To be Grothendieck rigid, you could, but then you could, but it's not it's easy to reduce to the injective cases. But you could, yeah. No, in fact, that's the way he said it, I think, is without injectivity. Okay, now is there anything to say here? Well, you might wonder, I'm going to talk. Yes, game on, right? There are full-sized hyperbolic groups, hyperbolic three-manifold groups that are profinite rigid in the absolute sense, right? So they're distinguished from all other finitely generated residually finite groups by their profinite completions. We only know finitely many for now. The list is growing, but we only know finitely many. Among the first ones, this Bianchi group, take PSL2 of Z, a join a cube root of unity. That's the first one we thought about. And then the ones we know are all fairly small, actually. So, and also the fundamental group of the smallest closed hyperbolic three manifold, the Weeks manifold. That's profinite rigid in the absolute sense, right? So not just among three manifold groups, but among all finite generated residually finite groups. So there are things to talk about in terms of absolute profinite rigidity, particularly in the context of three manifolds. And also going back, this is a warning that I'm going to come back to. And this isn't just nice history. I'm actually going to need some of the ideas from this. So back in 2006, so there do exist finite presented. Now I'm making a point of the fact they're hyperbolic here. That they're nice groups that you can put them in, that can make them special, for example. They're subgroups of SL and Z. They're finite presented, but they're not Grothendieck rigid, right? So you can construct finitely presented subgroups of infinite index. So they're not abstractly isomorphic to gamma even, but the map induces an isomorphism of profinite completions, right? So this is some infinite index subgroup, but when you look at the finite images of H cross H, that's infinite index subgroup always maps onto the whole thing. And that is and those are all the finite images of P of the subgroup. Okay? So even with some nice curvature, and even with nice matrices, you can find things which aren't profinitely rigid, even in this sort of weaker sense of the Grothendieck sense. Okay. Now, Zalil was making a point yesterday about sub-objects of direct products can be ferociously complicated, and that's going to be the theme here. Yeah. Yes, but not. But I don't know. Now, I think I don't know. I don't know one that isn't Grothendieck rigid with respect to finitely presented subgroups. So if I do, I'll give you an example. So if you do, this is related to something I'm going to say later, actually, but let's do it now because it's really good. If I do a RIPS construction and I make this a special I can make that a special group, in fact, right? So it's special. So in particular, it's in SLDZ, so it's really finite. And I do a RIPS construction. So that's going to be a two-dimensional hyperbolic group, like cohomological dimension 2. What I make this group so that H2 of Q with Z coefficients is 0, and it has no finite quotients, and it's got a finite classifying space. Well, I just type F3 is enough. That's the three-felt skeleton of its classifying space should be finite. I spent many hours making such groups. You can make such groups, okay? If you do a RIPS construction over that, then this is finitely generated but not finitely presented. And it's a little theorem that inclusion is an isomorphism, is a profinite isomorphism. Okay, so, and it's not finitely presented, so it's not hyperbolics. So there are examples of hyperbolic groups that aren't Grothendieck rigid, but here this is never finitely presented, right? And so I don't think I know an example with regard to finitely presented subgroups. Sorry? This is H cross H. Yeah, no, this is an important point. No, this is a good question. This is a good point, and it goes back to what Zalil was saying, that it's the sub-objects of direct products can be complicated, right? So that's very nice. Yeah, but yeah, this is a finitely presented subgroup of the direct product. Okay, so here's some guiding conjectures. Okay, right. So There's one we had before, finite generated free groups. They should be profinitely rigid, just hasn't been proved yet. I strongly suspect, and I think other people do too, in fact, all lattices in PSL2R and PSL2 should be profinitely rigid in the absolute sense. Right? So if you've got a mystery group with the same finite quotients as a Kleinian group, it should be Kleinian. And it should be that Kleinian group and no other. Okay. Now, regarding this last conversation about, I strongly believed, so if these are sort of general conjectures, this is, blame me for this conjecture, this is me. I strongly believe that F cross F is profinitely rigid amongst all finitely presented groups. Okay. Now, it's not among finitely generated groups. And that's why I think this is interesting. That's the point of this talk about the difference between finite generation and finite presented. Oh, I should just mention, in the case of PSL2R, we do know that if you stay within the class, you can distinguish two groups by their finite images. We don't know that in PSL2C. We don't know it for Kleinian groups, but there's a very nice paper of Liu in which he proves you only get finite ambiguity, finite genus. Only finitely many guys can have the same profinite completion.
What is this in SON1?
Yeah, things are wilder in SON1. This really uses low. Yeah, things break down in higher rank. It's in higher dimension. It's a good. It's very much an active field as to how much rigidity you get in other rank 1 Lie groups, including SON1. And in, I think Ryan's. Are you going to talk about this? Right? Yeah. Okay. So here's the theorem that I really want to talk about today. The new stuff. So I'm going to try and give you some ideas of proof, but let me not rush through the statement. So the idea is there's infinitely many non-isomorphic, finitely presented, residually finite groups, gamma, with a property that they're profinitely rigid amongst all finitely presented groups. Right. So I'd like to be saying this theorem about F cross F, but I'm not saying about F cross F. I'm saying about other finitely presented groups. So they're profinitely rigid amongst all finitely presented groups, but there's going to be infinitely many non-isomorphic, finitely generated subgroups of gamma that give you a Grothendieck pair, so that you don't get Grothendieck rigidity with respect to finitely generated subgroups. Okay, so, and moreover, every finitely generated residually finite group that you find in the gutter that has the same profinite completion as gamma actually arises as a subgroup. Okay, so there aren't these totally alien ones. You reduce to Grothendieck rigidity, but Grothendieck rigidity fails for finitely generated subgroups, and it holds for finitely presented subgroups. Is the statement clear? So you can see why I talk about those 3 types of profinite rigidity. Okay, and in this case, you can reduce to Grothendieck rigidity. Oh, and why am I doing this here? Because what are these groups going to be? They're going to be direct products of certain Seifert fibred spaces. Okay, with SL2R geometry. Direct products, though, not the Seifert fiber space themselves. Yeah. So no, already 2 tells you that. So 2 tells you that if I replaced finite presented by finite generated, it would be false. And 3 tells you that all of the counterexamples come from subgroups. Any other questions? Okay. Seifert fiber spaces. I presume you all know about Seifert fiber spaces, but there's no harm in showing a nice picture. This comes from an electrical engineering book, this picture. And it was an interesting article about the most efficient way to coil electric wires. And I was delighted to find it. So, of course, you all know, but let me remind you. So Seifert fibered space, so it's a 3-manifold foliated by circles, right? You collapse the circles to a point, you get a map down to a base surface, but those exceptional fibers with the winding from the electrical engineers give you orbifold, conical orbifold points here. So you get at the level of pi1, you have your 3-manifold mapping to a 2-orbifold group and a central Z, where Z is the generic fiber of the generic fiber of the fibration of the foliation. Okay. Now let me remind you something I said earlier. I said that Wilkes had proved that for all Seifert fibered spaces with geometry SL2R tilde, the fundamental group is determined by its profinite completion in that class. Right. So that's kind of telling us we've got some rigidity in this class. So I'm going to stick to Seifert fibered spaces. where this is a hyperbolic orbifold. They're going to be small hyperbolic orbifolds, actually. I'm using delta because I'm going to talk about triangle groups. And the Euler class is non-zero here. These are not finitely covered by products. Okay. And I'm particularly going to tell the whole story about this group, right? The 3, 3, 4 triangle group. Okay, and 4, 4, 4, because it makes some things easier. All right, so the Seifert fiber space is over 4, 4, 4 with non-zero Euler class. So what do you have? You have ABC, the generators of your triangle group. So this is supposed to match this, right? ABC, the generators of the triangle group. ABC, the generators of the triangle group. Z is the center. And then you just have to, so you're lifting the relations. So each relation here, a to the fourth, instead of being 1, is something central. And they do it with the other relations, and you have choices to what the exponents here are. Now you can fiddle with this, and you can see standard, you can normalize the Seifert data. So every Seifert fiber space over 4, 4, 4 is actually in this family where you have 3 1s or a -1 and 2 1s, and then an integer d there. Okay, that you can normalize the data like that. Okay, now I'm going to claim in a minute that these are all different profinitely, where you can distinguish between them by their finite quotients. Now Wilks tells me that anyway, but I'm going to do it in a very specific way. I was saying to Jason yesterday, I've had a lot of fun playing with magma with this. It's if you just do this, if you keep the same d and you change the -1, it's remarkable how similar those groups are, and they have the same finite quotients for a long way. But you can actually distinguish between them using certain mod 2 nilpotent quotient. So there's this thing which I think is sometimes called the Stallings lower central series, where you take the lower central series of your group, but you also kill, you can do it with any prime p, I'm going to do it with 2, you just kill all the squares as you go along as well. Okay? So Stallings considered this in his famous work on lower central series, right? So it's like the normal lower central series, but you're killing squares as well. That just means the squares in the subgroup. So this will give you some finite nilpotent 2 group, and magma has these routines in it that can handle finite p groups, right? So you can ask what certain groups are. And using that, you can prove this. And I want to say that because parts of this proof are very concrete. And here's an example, right? So for any Seifert fibered space over the 4, 4, 4 orbifold, it's completely determined by its abelianization and by the 5th term of the mod 2 lower central series. Right? So that's a concrete thing that you can actually sort of prove by hand with a little computer calculation. But you can't, these things are quite big. That's size 2 to the 17, right? It's always size 2 to the 17. And the point is that as you change the Seifert data, you change d, which group of order 2 to the 17 you get will change. Right? So this is how you can distinguish these with just these finite quotients. Now I need that because at some point in the proof, which I probably won't get to, I need, if you got 2 groups of this sort, not only are they different, but there's no way you can take one of those discrete groups and embed it in the profinite completion of the other with a dense image. So that's a stronger statement than saying they have the same different profinite completions, and that's crucial at some point in the argument to avoid sort of some possibility of a hop type phenomenon. Okay, so let me give you a more precise version of this theorem. So take G to be a Seifert fibered space. You can take any, there's different class of examples, but I'm going to stick to these. Take any Seifert fiber space over the 3, 3, 4 triangle group, the one I drew a picture of. Let gamma be a direct product of 2 copies of the fundamental group. Then you have these 3 things. It's profinite rigid amongst finite presenter groups, not among finite generated groups, but all the counterexamples come from subgroups. Okay. Now, how are we going to, and there's similar theorems with some extra technicalities over other rigid base orbifolds. Now, I haven't told you what a rigid base orbifold is yet. That's on the next slide.
Do you care whether G is something that has SL2R or
in this case, they all have SL2R geometry. You see. In 3, 3, 4, there's, because the Seifert fiber space has to have no torsion, and so you can't, and all the torsion-free central extensions by Z are actually SL2R tilde geometry here. Now that's a good question. I do have to avoid H2 cross R in other cases. Okay, now how's this going to go? So I say I'm not going to be able to give you the proof, but I do want to give you some of the ideas, and that should be possible. If I can remember the code to my phone. So first of all, I have to explain what's special about 334. Why am I doing 334? It's got something to do with this rigid base orbifolds. I'll come back in a second. What is going to happen is 334 is profinitely rigid in the absolute sense. That's the starting point of this. But then I have to extend that rigidity to handle central extensions with a Z. And then how are we actually going to get this reduction? So instead of talking about absolute profinite completions where you just got groups defined in the gutter, how are we going to reduce so that everything is in this Grothendieck rigidity context, that all the examples you have to worry about are actually subgroups? I want to explain that. And I particularly want to explain why the finiteness properties make such a difference, right? That won't remain a mystery at the end of the talk, I hope. Okay. Right. So first, this thing about why am I using 334? And it's because it's on this list. So these are, so I told you, I gave you a couple of examples, a Bianchi group and the Weeks manifold of compact, it's not compact, lattices in PSL2C that are profinitely rigid in the absolute sense. You can also find some in PSL2R, right? And the ones we know at the moment are all on this list. Okay, so these are all triangle groups. They're triangle groups, so they're all profinitely rigid in the absolute sense. And 334 and 444 hopefully are on this list. There's 334, there's 444. So this is what Ryan's going to talk about. So how do you, let me just say a few words about how you prove those are profinitely rigid in the absolute sense, because it gives a sense of the sort of mathematics that's involved. First of all, they're triangle groups. So they're very rigid things, right? Unlike other Fuchsian groups, they don't have Teichmuller spaces. They have very few representations. And in fact, for these lists, there's some arithmetic data that's important. They all arise as the image of the norm one elements in a maximal order in a quaternion algebra over a real quadratic field that ramifies in a certain way. And then there's some machine called Galois rigidity that Ryan's going to talk about. That's arithmetic. It's the arithmetic of these groups that makes them rigid. And I'll say a little bit more about that in a second. But the first theorem we prove in this more recent project is that for infinitely many, but not all of the Seifert fibred spaces with a profinite rigid base, that is any of those bases, the fundamental groups of the Seifert fibred spaces will also be profinitely rigid. Now for 334, the proof works for all of them. For other rigid bases, there's some technicalities that we can't prove it for all of them. So what am I saying? I'm saying these are profinitely rigid groups. Take a central extension, it stays profinitely rigid. Okay. If the central extension is by Z, but it really matters it's Z and you stay in the world of three manifolds. So I have a student, Pavel Pivek, who proved that the argument breaks down if you replace the Z center by Z squared. That should say no, thank you. It's not true for arbitrary central extensions, right? It's more subtle than that. It really matters that there's Seifert fiber spaces. Thank you. Okay, so what are the key steps in proving this? The first is, and this comes back to the question about so what's the connection here? What you first prove is item 3. Right. First of all, you reduce to the Grothendieck rigidity situation. You prove that you find a group in the gutter with the right finite images, then actually you're going to construct a morphism from your mystery group into your classical group gamma. Okay. And it's going to be an injective morphism induces the profinite completion. And then we'll have reduced to the Grothendieck rigidity situation, and we'll be able to use things that say we're inside a nice situation, a product. We know the mystery group is actually a subgroup of a product of Seifert fibered groups. Okay. And then, so that's step 1 to get the group from the gutter inside gamma, which is G cross G. And then obviously the second step is to prove that G cross G is Grothendieck rigid amongst finite presented groups, but not amongst finite generated groups. Right? So that's the first level of proof. Those are the 2 steps we're going to do. Let me start with number 1. Now I'm going to go over this very quickly because Ryan's going to talk about very related things. Okay, this is where the, or did I say what sort of maths? No. This is Galois rigidity. So what makes these finite lists of things? How do you get control? The key point is their controlled arithmetic. So I really am going to say this quickly. Yeah. you say a group is what's special about dimension 3 hyperbolic groups that isn't true in SON1 for higher rank, for example, is you have this arithmetic. Even if your lattice isn't an arithmetic lattice, you have the arithmetic of the trace field, right? So you've got a representation of your group into SL2C. You can just take the traces, join those to Q, you get some number field, right? If you've got a lattice. Now, if you've got one lattice sitting inside SL2C, so as we were hearing yesterday, you can do interesting things by taking Galois conjugates, right? So the number field is generated by some primitive root theta. Taking the Galois conjugates of that will give you different embeddings of your original group coming from the different field embeddings of the trace field. Right? So if you've got one representation, you'll always get a bunch of others coming from Galois conjugates of the trace field. You say something is Galois rigid if there are no other representations, if the arithmetic explains all of the representation theory of this group into SL2C. Right? And these groups that we prove are Galois rigid have that property. Okay? So that's the key idea. It's a little bit tricky because you don't work with C representations. You actually have to work over the algebraic closure of the p-adics to get sort of local representations. But there's a really beautiful machinery there that's absolutely behind these profinite rigidity theorems for these arithmetic lattices in SL2R and SL2C. Okay, so I said that very quickly, but the point is arithmetic, right? That part of the proof is all about arithmetic and representation theory. Now, that was about groups embedding in SL2C, but now we're going to take central extensions of them. But now, suppose you take a central extension of, say, a lattice in SL2C. How can that central extension map to SL2C? Well, if you've got a non-elementary subgroup of SL2C, then as you all know, it's got no center there. We're in rank 1, right? So the center is actually basically going to have to die whenever you. So the representation theory of a central extension of a Kleinian group into SL2C is essentially going to be the same as if you hadn't taken the central extension. The central extension is just not going to do anything. Okay, and likewise, if you take a direct product of two things, you try and represent that to SL2C. Well, the first one says, "Well, I'm not commuting with him," and the other one says, "I'm not commuting with him." So one of them has to die before they get there, right? Otherwise, there's too much commuting. And so the representation theory of a direct product into SL2C is also basically the same. So if you can control how you map these profinite rigid groups to SL2C, then you should also be able to control central extensions and direct products, because it just doesn't do anything, right? The direct product will factor into representation of the first factor and representation of the second factor. So because of that, we take these Seifert fibred spaces over our rigid triangle groups, and if you have a mystery group with the same profinite completion as G cross G, then by looking at the SL2C representation theory, you'll be able to get this mystery group from the gutter to map to a direct product of two copies of your rigid triangle group, okay? Which is moving us towards Grothendieck rigidity, crucially, right? Except I'm trying to get the mystery group into G cross G, and what I've got it into is delta cross delta. So there's going to be a lifting problem, right? Which is some extra work, but you solve that lifting problem. And I think I'm going to skip over that because you can see at least what you have to do, right? You've got it down into delta cross delta. You have to lift it up into G cross G. And that's where I made this comment before about controlling which things densely embed in other things, and that comes into this part of the argument. Okay, I'm gonna skip over that, I think. Okay, and I want to, because now I want to spend the last few minutes, 6 minutes and 2 seconds, explaining why finite generation versus finite presentation is important. Okay, so this is a moment where you can wake up or go to sleep. And so here's a sample theorem, right? So now I'll switch from 334 to 444. No, so now I'm going to work over the 444 triangle group. I could be working over the others, but I'm working over this one. I'm taking Seifert fibered spaces over the 444 fold. And I claim the following, right? So gamma is always the direct product of two copies of the fundamental group. If you got a subgroup that's finitely presented, then let me say it in other words. I'm going to say that G cross G is Grothendieck rigid amongst finitely presented subgroups, but not amongst finitely generated subgroups. Right? That's what I want to say. Spelling that out, if I've got a finitely presented subgroup of G cross G, then if I take the closure and the profinite completion, you'll never get the whole thing. It can't be dense. Okay? But you can make infinitely many non-isomorphic finitely generated subgroups in G cross G, so that the inclusion gives you an isomorphism in profinite completions. Right? So this is where you see the difference between finite generation and finite presentation. Okay? And I want to explain to you why, because it sort of relates to limit groups and things Leo was talking about yesterday, tangentially. So the homological algebra in this situation is much harder, but the main ideas really go back a long way. They go back to Platonov and Tavkin and what I did with Fritz Grunewald, and then some work I did with Henry Wilton that's related to this paper. Right, and so rather than go into the technicalities of that theorem, I'm going to explain the toy model to you. Okay, and the toy model is that remember my conjecture that F cross F is profinitely rigid amongst finitely presented groups. Now, if I take a free F as a free group or surface group or triangle group or Fuchsian group, then it is known that F cross F is Grothendieck rigid amongst finitely presented groups, but not among finitely generated groups. Okay, so on the previous slide, I was proving this for these Seifert fiber groups, but I'm going to explain the proof to you for F cross F. Okay, because that's really where these ideas come from. Now, what's the key fact? The key fact is that there's lots of bad subgroup finite generated subgroups of F cross F, but there aren't any bad finitely presented subgroups. More specifically, if you take a free group or any lattice in PSL2R, and this works for limit groups as well, and that's really where the idea comes from, then every finitely presented subgroup of a direct product is closed in the profinite topology, right? All of them, right? They're all closed. So in particular, that means it can't be the whole thing, right? So in particular, there's no Grothendieck pairs with finitely presented subgroups. Now, why is that true? Well, it's buried in the results about the structure of residually free groups and what the finitely presented subgroups of a direct product of limit groups can be. That's which use a lot of technology, sort of tower technology that Leo was talking about yesterday. Okay, but where do the wild things come from? Where are the wild things? Where do these bad finitely generated subgroups of F cross F come from? And this goes back to this discussion over here about building short exact sequences like this. Right? So I claim, and I'm going to sketch for you why it's true, that there's infinitely many finitely generated subgroups of F cross F, so that the inclusion gives you an isomorphism of profinite completion. And how you do this is just what I was doing over there, only it's easier, right? You make designer groups. The design is you make a finite presented group with a finite classifying space, no finite quotients, and second homology being 0. I should say the group should be non-trivial as well. But it's, you make such a thing, you map a free group onto it, you take the fiber product, you take the pairs in F cross F that have the same image in Q. It's an easy exercise that you can just do, but that's a finitely generated subgroup. It's never finitely presented, but it's finitely generated subgroup. Okay, it's never finitely presented, but it is finitely generated. And the point is, if you think profinitely, right, Q profinitely is trivial. So this is like taking a fiber product over a point. So, if you take a fiber product over a point, you just get the whole thing, right? It's the pairs that have the same image under the trivial map. This would be the whole of F cross F. Well, it's not the whole of F cross F, but if you put hats on, it is. And that's really why you expect this why you expect this map to be an isomorphism. Proving it's injective is much trickier, and it needs, see, it heavily needs this fact, and no, it heavily needs this fact. Okay. There's some homological argument there. Now, I'm just going to do that again, right? You've got a trick, you've got a hammer, you just keep looking for nails, right? Instead of mapping the free group onto groups like this, I'll just build a sequence of groups with these properties, and I'll map my favorite triangle group onto them. Now, you can sort of use small cancellation theory. Olshansky did this. So given any non-elementary hyperbolic group, you can build a sequence of quotients so that the quotients are finitely presented, have no have no finite images. You can keep them of type F3. But what I don't see how to do is to keep them having H2 0. That seems to me very hard because you're adding relations. So intuitively, you're increasing the second homology, right? So I don't see how to do this and keep H2 0 always. Now, in the free group, it didn't matter because if you got a map of a free group onto a group, then you can lift that to a map onto the universal central extension because the free group has a trivial H2. You can't do that if your hyperbolic group has H2. And so you have to do some much fancier homological algebra, and that's what's here, to get around that problem, to let delta be a non-elementary hyperbolic group, and I'm thinking of a triangle group. Suppose you've got some other group that maps onto it. I'm thinking of that as my Seifert fibred manifold. Suppose H2 of that thing, the Seifert fibred manifold, 0. That we're going to arrange using Poincare duality. Now you've got some mystery group that maps onto the commutator subgroup of lambda. Now it's getting technical, and there's no coffee yet. Then this argument works. Okay, so there's some fancier homological algebra that lets you get around this problem, but it imposes some conditions on your groups, and that's what we do here. Roughly speaking, for our Seifert fibered spaces of these rigid orbifolds, we make it conform to this fancier version. You make it conform to the homological algebra you need, and that's how you build these Grothendieck. That's how you get these Grothendieck pairs. And as for F cross F, you have this discrepancy between finitely generated and finitely presented. Okay, so that's the theorem again. Thank you very much for your attention. Oh, it's a horrible technicality. So there's different, as you probably gather, there's lots of different parts to this argument, right? And so there's a lot of jigsaw stuff going on. But a really irritating thing that is a real it's to do with, right, so this calculation, there's two things that go wrong. So one is way back here, I said I did these magma calculations and I had these very simple invariants. And I had this crucial fact here. This I can't always do with the others. There's this horrible possibility that you have two Seifert fibered spaces over the same rigid base. And you know they're different, but maybe one injects in a dense way in the profinite completion of the other. Now that probably never happens, and it's certainly you can reduce it so it only happens sort of finitely often, but that's one irritation. It's truly just a technicality, but that's what goes wrong. So this sort of calculation works with 444 and 334 and some others like 335, but it doesn't work for them all. Right? So there's some finite ambiguity there. The other thing, which is a really silly, stupid thing, is at some point in the argument, you want to make the group you're interested in the commutator subgroup that has finite index in some other group that has some properties. And in most cases, I can do that, but there's a couple of cases where you can't. So there's a couple of algebraic technicalities, I would say. I don't believe they lead to counterexamples. They're just algebraic technicalities at that level. Yeah, that doesn't make a big same story. Yeah, as long as the rank's at least 2 in both factors, it's the same story.
Is finitely rigid among F3 but not F2.
No, I suspect that's already profinitely rigid amongst finite presented groups. I think so, yeah. So I said the conjecture for 2 factors, but I don't think you need higher finiteness properties. Oh, do I? No. See, the point is, so that theorem about residually free groups, it works for any number of factors. So you take a direct product of any number of free groups. Every finite presented subgroup is closed in the profinite topology. So I think I said it for 2, but I'd conjecture it for any number of factors with finite presentation as the condition.
So you said the finitely presented groups are closed in a profinite completion, but what about the non-finitely generated but not finitely presented? Some of them are not closed.
Some of them are closed and some of them aren't. Yeah. So the ones obtained by fiber products of sequences like that are not.
Maybe a silly question, but is it known if residually finite hyperbolic groups are Grothendieck rigid with respect to quasi-convex?
Yeah, because the quasi-convex subgroups will be closed in the profinite topology. So, sorry. Yeah, all the ones we love are. No, sorry. I would guess not, but I don't see why not. Yeah, so for virtually special ones, not. But yeah, in general, I don't know. I guess that's right. In general, I guess we just. Yeah, again, if we can't prove they're residually finite, then we can't prove this, I guess. Yeah. So.
So let's save any remaining questions for the break. Let's take them out.